Today we're doing the AP Physics C E&M FRQs. These are the released ones. They just released, so yeah, I'm gonna be doing them. Number 1. Okay. Isolated air-filled charged capacitor consists of two conducting coaxial cylindrical shells. Each have a length L. Inner shell has a radius R. Outer shell has a radius R2. Okay, so it's a cylindrical capacitor question. Absolute value of the total charges on the shells are equal. Okay, so the net charge of the entire thing is 0. It's good to know. Okay, so we have number 1. Use Gauss's law to derive an expression magnitude E in terms of R1 between R and R2. Okay, so we have surface integral E dot dA equals Q enclosed over E sub 0. And that reduces to E times A, which equals Q enclosed over E sub 0. And then we have our sigma 1, which equals your Q enclosed or your R1, like total enclosed charge divided by your enclosed area. So we're gonna say our enclosed area is the R1 area, and our Gaussian surface has some radius R, which is between R1 and R2, right? So we have E equals, and then your sigma A equals Q enclosed. Yeah, we're gonna sub that in. E equals sigma 1A over, well, that's gonna be your A1, and then this could be your A2. A1 over A2, E sub 0. Your A1 is just 2 pi R1L. That's divided by 2 pi RL times E sub 0. Cancels, all this cancels, and this is just sigma 1 R1 over R times E sub 0. Yeah, that's your expression for E. And then number 2, part 2. Derive an expression for the absolute value of the potential. Okay, so we're going the absolute value of the potential. So it's just the negative integral. Well, we know the potential is the negative integral E dot dr. And between the okay, so we're using this R1R less than R2. So we're gonna sub in this equation for electric fields into this. So the change in potential equals your negative integral sigma 1 R1 over R E sub 0 dr. And your change in potential is just negative sigma 1 R1 over E sub 0 natural log. And we go from R1 to R2, of course, sorry. Natural log R2 over R1. And your absolute value of potential is sigma 1 R1 over E sub 0 natural log R2 over R1. And yeah, that's it. It's the expression for your potential absolute value. Part B. Actually, never mind, sorry. Part 3 of part A. Okay, graph. Graph the electric field as a function of radius. Okay. That's R1, R2. So from 0 to R1, it has to be 0. Then it will shoot up, decay function, and it'll land somewhere. It's not gonna go to 0, it's gonna land somewhere here. It's gonna be a decay function, so exponential decay, I think. Right? Yeah, it should exponentially decay. And then it should be 0 because, yes, because we found that the total charge was 0, because it says that the absolute value of the charges on the shell are equal and the surface charge densities are opposite signs. That means the total charge has to be 0. So, and because if you, let's say you enclose the entire thing in a Gaussian surface, that would make the Q enclosed 0, so your electric field is going to be 0. The material of dielectric constant K is inserted. Okay. Charge capacitor such that part B. Derive an expression for the capacitance of C. Material inserted LR1, R2K, and physical constants as appropriate. Okay. With a fundamental physics principle. So we have C equals Q over change in V. Yeah. And your C equals your charge. And I mean, it's just sigma 1 equals your charge over E sub 0, right? Oh, not E sub 0, sorry, area. So sigma 1 times 2 pi R1L equals your Q. So that's just sigma 1, 2 pi R1L, and then divided by this expression, your change in potential, right? And so that would be negative sigma 1 R1 over E sub 0 natural log R2 over R1. And C equals, that cancels, that cancels. So it's 2 pi E sub 0 L over your natural log R2 over R1. And then you just add your dielectric constant. So you just add kappa to it. So your final capacitance is just 2 pi E sub 0 L kappa over natural log R2 over R1. Okay, yeah. And I think this is very obvious, and you can recheck this if you memorize the equation for the capacitance. It's just 2 pi times E sub 0 H over natural log B minus B over A. And yeah, it matches that, so you know you're fine.